It often seems as though computers must understand us because we understand the information they produce. Computers recognize two distinct physical states produced by electricity, magnetic polarity or reflected light. Essentially, we understand whether a switch is on or off. In fact, the CPU, which acts like the brain of the computer, consists of several million tiny electronic switches called transistors. A computer appears to understand information only because it operates at such phenomenal speeds, grouping its individual on and off switches into patterns that become meaningful to us. From a very early age, we are introduced to the concept of numbers and counting. Toddlers learn early that they can carry two cookies, one in each hand. Kindergartners starting by twos and fives. Invariably, we use the decimal number system. A number system is based on 10, most likely because we have 10 fingers. A number system is simply a matter of counting. Many different number systems exist. Consider a clock. Clocks have 12 hours, each composed of 60 minutes. Each minute is composed of 60 seconds. Computers, like clocks, have their own numbering system, the binary number system. To a computer, everything is a number. Numbers are numbers. Letters and punctuation marks are numbers. Consider the following sentence. Here are some words. This sentence may look like a string of alphabetic characters to you, but to a computer, it looks like a string of ones and zeros. Look at the attached picture. When referring to computerized data, the value represented by each switch state, whether the switch is turned on or off, is called a bit. A bit is a combination of binary digits. A bit is the smallest possible unit of data a computer can recognize or use. A group of 8 bits is called a byte. Half of a byte is called a nibble. The byte is an extremely important unit because there are enough different 8-bit combinations to represent all the characters on the keyboard, including all the letters, numbers, and other symbols. Early programmers realized that they need a standard text code that was agreeable to all of them: the EBCDIC, ASCII, and the Unicode. And now, I will introduce to you the 3 common text codes. First, we have the EBCDIC. EBCDIC stands for Extended Binary Coded Decimal Interchange Code. It is an 8-bit code that defines 256 symbols. It is still used in IBM mainframe and mid-range systems, but it is rarely encountered in personal computers. Next, we have the ASCII. ASCII stands for American Standard Code for Information Interchange. Today, ASCII character set is by far the most commonly used in computers of all types. It is an 8-bit code that specifies characters for values from 0 to 127. Last, we have the Unicode. The Unicode Worldwide Character Standard provides up to 4 bytes, 32 bits, to represent each letter, number, or symbol. 2 components handle processing in a computer: the central processing unit, or CPU, and the memory. Both are located at the computer's motherboard. The CPU is the brain of the computer, as I have told you last time. It is a place where data is manipulated. In large computer systems, such as supercomputers and mainframes, processing tasks may be handled by multiple processing chips. So every CPU has at least 2 basic parts. We have the control unit and the arithmetic logic unit. All the computer's resources are managed from the control unit. The CPU's instructions for carrying out commands are built into the control unit. The instructions or instruction set list all the operations that the CPU can perform. So each instruction in the instruction set is expressed in microcode. So ang microcode, it is a series of basic directions that tell the CPU how to execute more complex operations. The computer can perform two types of operations: arithmetic operations and logical operations. Arithmetic operations include addition, subtraction, multiplication, and division. Logical operations include comparisons, such as determining whether one number is equal to, greater than, or less than another number. Many instructions carried out by the control unit involve simple moving data from one place to another, from memory to storage, from memory to the printer, and so forth. When the control unit encounters an instruction that involves arithmetic or logic, however, it passes that instruction to the second component of the CPU, that is the arithmetic logic unit, or ALU. The ALU performs the arithmetic and logical operations. The ALU includes a group of registers, high-speed memory locations built directly into the CPU that are used to hold the data currently being processed. Each time the CPU executes an instruction, its series of steps. The completed series of steps is called a machine cycle. A machine cycle itself can be broken down into smaller cycles: the instruction cycle and the execution cycle. At the beginning of machine cycle, that is, during the instruction cycle, the CPU takes two steps. First, we have the fetching. Before the CPU can execute an instruction, the control unit must retrieve or fetch a command or data from the computer's memory. Next, after fetching, we have the decoding. Before a command can be executed, the control unit must break down or decode the command into instructions that correspond to those in the CPU's instruction set. At this point, the CPU is ready to begin the execution cycle. So, nanata sa executing nga phase. So, sa executing a phase, when the command is executed, the CPUs carried out the instructions in order by converting them into microcode. So, muna siya ang executing ng phase. Next, after executing, storing. So, the CPU may be required to store the results of an instruction in memory. Although the process is complex, the computer can accomplish it in an incredible speed and translating millions of instructions every second. In fact, the CPU performance is often measured in millions of instructions per second. And then now we have a latest versions of CPU. So newer CPUs can be measured in billions of instructions per second. So inaana kapaspas ang ato ang speed sa pag-travel sa mga data sa ato ang computer. To sum it up, data is information. Data can be numbers, strings of characters, or images. All data must be entered into the computer for it to be processed. Data can be read out of a file, typed in via the keyboard, or scanned in like a barcode. From a computer programmer's viewpoint, this is considered raw data that needs to be processed. Computers process very large amounts of data because they can interpret the data much more quickly than a person. Most data processing is mundane and would be prone to human error if not processed by computer. Computers process data so fast that their speed is measured in MIPS, millions of instructions per second, as I talked earlier. A computer uses a central processing unit or CPU to do all its decision-making and data processing. The CPU has an eternal set of instructions it follows when it receives a command. Programmers use different languages to give the CPU commands. These languages are more human-readable than the CPU's machine language. The CPU follows the programmer's logic to process the data given it. There are two types of built-in memory. We have the permanent memory and non-permanent memory. Some memory chips retain the data they hold even when the computer is turned off. This type of permanent memory is called non-volatile. Other chips lose their contents when the computer's power is shut off. This type of non-permanent memory is called volatile. Non-volatile chips hold data even when the computer is unplugged. The data in these chips is called read and used, not changed, so the memory is called read-only memory. Volatile memory requires power to store data. The volatile memory in a computer is called random access memory. RAM's job is to hold programs and data while they are in use.